Let me exemplify how maximum likelihood works, or show you how it works for the normal distribution. The distribution that we use as an assumption for a lot of what we do in a basic stats course like this. So let's just have a feeling about how that actually works. So we would assume the classical model here, for instance, that we have independent observations stemming from the normal distribution with some mean mu and some variance sigma squared. That is the density of xi. We have mu and sigma squared in the density would be 1 over square root 2 pi over sigma e to minus, let me see if I can remember, xi minus mu squared divided by sigma squared. This is the density function for the normal distribution with mean mu and sigma squared. What is then the likelihood function? The likelihood function as a function of mu and sigma. It's a decision whether you want to see it as a function of sigma or sigma squared. I choose sigma now. The likelihood function would be the product of the independent observations of this one, of course, that I just put in here. Let me just put it again. Square root 2 pi sigma e to minus xi minus mu squared over sigma squared. I take the log to go for the log likelihood function. Log L, capital L, mu sigma. So it becomes a sum, and then I go to take the individual terms now. It becomes the sum of I up to n. It becomes minus log square root 2 pi. It becomes minus log sigma. That's the first part of it. Then the exponential sort of cancels out, you could say. So it becomes minus xi minus mu squared over sigma squared. That is the log likelihood function of the normal distribution. How to find the maximum likelihood estimators of mu and sigma? Well, we would start to take the derivative of the log likelihood function with respect to mu as a first thing here. So we look at this one and look at where do we have mu. Well, here and here we don't even have mu at all, so they become 0 when we take the derivative with respect to mu. Only this term depends on mu. So I take the derivative here, and let me see, I maintain the sum. I put the minus there, sum from I up to n. Then I take the derivative. That then becomes 2xi minus mu divided by sigma squared. That's the derivative with respect to mu. Now if I equate this with 0, then I see the sigma squared vanishes, and basically I see what I hoped for, that if I solve this, the 2 also disappears, and I am left with the fact that we should estimate the MLE estimate, the maximum likelihood estimate of mu, would be, luckily, the average. Actually, I missed something here. Sorry about that. No, actually, it's because I have the sum here, and the sum goes with the mu to produce n times mu, and this is why we have the sum of the x's to be divided by n to produce what we already knew. In a way, the way we estimate the mean and the normal is by computing the average of x. Let us see what the result is. What is the maximum likelihood estimated for sigma MLE? Let us have a look at that. Well, we take the derivative of this one with respect to sigma, and we have a couple of terms now to look at. Again, this term disappears. This term becomes, I maintain the sum in first row here, first step. Then I get the minus 1 over sigma, right? That's the derivative of the log. And then what about the second one, this term here? This term, I get the derivative. That is then 1 over sigma squared. Basically, that I take the derivative. So that is using the rule. Let me see. This is like sigma to minus 2. So I, again, if I maintain the sum, I maintain the minus. I maintain the constant. xi minus mu squared is a constant. I take the derivative of sigma to minus 2. That's a minus 3 times sigma to minus 3. That's a rule of taking the derivatives of powers. In this case, sigma to minus 2. Then I equate this with 0, and I try to solve for sigma. Let us try to do it a bit step by step. We take the first thing here. That becomes minus n over sigma. What about the second step? We have, let's see, we have a minus and a minus. So that becomes a plus. We have the sum of xi minus mu squared times, you could say times, let's say, 3 over sigma to the third, if we go like this. Let me see, I think I have, I did a mistake here actually. I did the mistake that when I took the derivative of sigma squared, I should have not set minus 3, I should have set minus 2, of course, because it was sigma to the minus 2, so I take minus 2, so I use the rule for the derivative a bit wrong, so I have a 2 here, sorry about that, rather than a 3. Now, actually, I've done another little mistake because I forgot a 2 up here. Actually, in the beginning, there is a 2 there as a part of the density function. So this one I need to carry on with. And it has the lucky effect that this 2 that I forgot from before will cancel out with the 2 that I just had here. Then if I'm going to equate this with 0, and I multiply through by sigma, let me see, sigma to the power of 3, I will see that this one corresponds to that n times sigma to power 2 would equal the sum of xi minus mu to the power of 2. Then mu I estimate by sigma hat. Sorry, mu I estimate by the average, as I saw from my previous computation up here. So if I plug this in, I now see that the maximum likelihood estimator of the variance I divide by n, and I plug in the maximum likelihood estimator of mu, and I get the maximum likelihood estimator of the variance using the normal distribution, with the bit funny and interesting result that when we find maximum likelihood estimators of variances in the normal model, we actually get the result that we, in this case, would suggest us to divide by 1 over n. Even though we, in most practical purposes, we don't use the 1 over n, we would use 1 over n minus 1. And this is not a discussion for here. But this is actually the maximum likelihood estimator of the variance. Thanks.